Welcome everyone to our next Thursday research seminar. Our speaker today is Dr. Stefan Launer. Stefan is a vice president at a large international hearing aid company called Phonak, and he's vice president for advanced concepts and technology. Okay. So Stefan has, now the easy bit. So Stefan has a background in physics and medical physics. Did a PhD in loudness perception in hearing impaired individuals, and then, as I say, for about 20 years has been working with Phonak, who are Swiss company and based in Switzerland. So he's a good friend and ally to the department. Stefan's been involved in collaborating on a number of projects, funding some PhDs. So I think Anne-Marie's not here right now, but Anne-Marie Hamilton, one of our PhD students, is funded by Phonak. So it's great that Stefan's come back to spend the day with us, cramming everything in, and in amongst all these meetings with individual members of staff, he's agreed to do this presentation for us today on wireless technologies. So we were already familiar with some wireless technologies, remote microphones to help improve signal to noise ratio if someone's talking at the back of the class and you want to hear them at the front. But there are other applications as well, applications where we might want one hearing aid to talk to another hearing aid, which might just be convenient for someone instead of altering the volume control, but it might also improve performance, or it might involve someone with a hearing aid being able to use it with their iPhone, for example, or sat-nav. I'm guessing that some of what I'll sound might be part of Stefan's presentation.
You did half of my talk. Thank you for the introduction and for the invitation to present on wireless technologies for improving speech intelligibility in hearing systems. And this is not a huge auditorium, so I would really encourage you, if you have questions along the way, if you have points to discuss, I would be happy to take them and answer questions or have discussions on the way. I would like to talk a little bit about wireless technology and about two different applications of wireless technologies in hearing instruments. One is, what can we do if we connect the two devices with each other in terms of improving speech intelligibility? And the second is, what can we do when we have larger distances, and what are the applications there? But to begin with, I would like to point out where we have come with digital hearing instruments. And I would like to use 4 slides to show you how the complexity of hearing instruments has changed over the past years. And basically, the schematic of the slide is always the same. You have 2 microphones as input here, and the loudspeaker as the output here, and all the gray building blocks in between represent algorithms like the noise canceller, the gain model, classifier or environment control, the beamformers, and then you see the connections in between them. And now in the next 3 slides, I don't talk, I just show you how the complexity has changed over to today. That's today's generation, and today's generation you can actually copy this and map it, because both hearing instruments talk to each other and are connected. And one thing that people often don't see when we talk about innovation in hearing instruments is that we have introduced a lot of new functionality in the hearing instruments over the past decade. But what we also did is we made all the functionality we already had, the noise cancellers and the beamformers, work in more and more and more and more environments. So take a directional microphone. Like 20 years ago, it was optimized in its performance to work in a sound-treated room with a single target coming from the front and an interfering white noise coming from the back. But as soon as you put the noise a little bit to the side, the performance of the directional microphone would break down. And today, our systems work in far more conditions in daily life. So you have a noise canceller that works for many different types of noises and creates much less artifacts. And that's why we needed much more interaction between the algorithms and much more additional building blocks. But that's something that is very hard to tell, that it's not only adding new functionality, but it's also expanding the scope of the already existing functionality that has improved over the past years. I think today's hearing instruments and most of what I talk about today is equally applicable to cochlear implants, basically, because the pre-processing in the devices, say in the next 5 years, is going to be very similar, if not identical. It's converging a lot. So in the hearing instruments, we have basically 3 sets of algorithms. One set of algorithms simply is targeted at cleaning the sound from artifacts, cleaning the sounds from interfering noises or interfering sounds, and making the sound be realistic and natural and authentic also in terms of localization. That's one set of algorithms. Noise cancellation, feedback cancellation, different environments, impulsive noises, wind noises, reverberation and stuff like that. And then we have a second set of algorithms which basically simply amplify the sound or make the sound audible. And here recently frequency lowering has been introduced, and that's one of the most hotly debated topics. Very interesting to follow because basically today almost every hearing instrument from every brand has some form of frequency lowering techniques built in, and that was interesting for me to observe how that really kind of spread out and became pretty standard. In terms of amplification, we all have multi-channel compression systems. Now, as I said already, this processing can be the same, and then you have an acoustic or an electric output to stimulate a hearing instrument or a cochlear implant. And in between, because we have multiple algorithms that serve multiple different listening conditions, you need kind of an intelligent environment control that takes the decision to switch on or switch off algorithms. So we have pretty sophisticated systems today that allow the hearing instrument to identify an environment where a person is in and to select a subset of algorithms that is available and to offer the optimal signal processing for a given condition. That's basically what the hearing instruments almost all have today. And I want to skip this one. What can we add when we add wireless communication? So we have one hearing instrument with all the signal processing that I just mentioned, and suddenly we have another hearing instrument on the other side. When we talk about wireless communication, we basically have 2 different applications we can use wireless communication for. One is improve performance and intelligibility with wireless communication. The other one is add connectivity and add services, add functionalities that we don't have today, like remote control, better control over the devices, read out data, information and stuff like that. So we have these 2 applications, the communication and the connectivity. And when it comes to communication, we basically have 2 different sets of systems. One is a system on the body that connects the 2 devices, and one is a system that allows to directly stream in signals from the outside world to the hearing instruments over a larger distance or from other sources. So when it comes to looking at hearing instruments with wireless communication abilities, it's always extremely important to not just say, yeah, this is a wireless hearing instrument, but it's very important to say, and what is exactly the use case that you want to solve? What is the problem that you want to solve? Because today, a lot of wireless connectivity and the discussion around it is streaming external sounds into the device, and much less talk is about really what can we do to help people in their daily life environments to improve speech intelligibility. And there are various systems around. Today, for the long-range communication, we still have a separate system from the binaural communication that is used. It's different radio technologies that are being used. There is not a single technology available today that could do both on-body communication and long-range off-body communication. It's 2 different radios that you need for that. And when you want to compare them, it's important to consider what was the system actually designed for. So one point is, what can we use the 2 ears for? And I had to do a talk on animal bioacoustics 2 years ago, and I realized that, and it might be stupid, but I was still stunned that almost every animal has 2 ears, not 1 and not 4. Almost every vertebrate just has 2, and that seems to be an optimum, except for the insects. They have 6 and an arbitrary number of ears, but all the others only have 2. And what do we need these 2 ears for? Basically, my understanding today is that using 2 ears provides different advantages. One big advantage that is often talked about certainly is we can use 2 ears to localize a sound. But, and this is something I put out also for discussion, I'm not entirely sure whether this precise localization mechanism really helps us to improve speech intelligibility in noise, because there has been some remarkable work by Stuart Gatehouse and others which showed that actually in noise people aren't very good at localizing. They lose the localization precision. Still, 2 ears, we benefit from having 2 ears, but it's not this precise localization mechanism. It has to be something else, focusing attention or something. So localization is one thing in free field why we could use 2 ears, but there are 2 other advantages, and one is that in certain listening conditions we simply select the better of the 2 ears, and we almost discard the input from the other ear. There was a very nice study by Monica Hawley and Steve Colburn which showed that especially when the target is to the side, you gain most in terms of speech intelligibility by listening through the better ear. If you added the second ear, you also gained a little bit more, you improved, but the big step was going to the better ear. So in certain listening conditions, this is already a pretty clever strategy to do. And then in other listening conditions, especially when the target is in front and the sources are distributed, listening through 2 ears provided the best input. So our auditory system seems to apply different listening strategies for different listening environments. And that was basically a guiding principle for us to design a binaural signal processing strategy that would mimic that. If you have 2 hearing instruments and they can transmit the audio signal between each other, you basically start having a network of 4 microphones. And with 4 microphones, you can do a pretty good directional microphone system. But there is a different thing that you can do. The other thing that you can do is you can simply apply this trick of listening through the better ear and listening through the ear on the correct side. So for example, in a car environment, when the person, you are typically in a speech in noise condition, and speech in noise, every hearing instrument would actually immediately say, yeah, let's switch on the beamformer. But in a car, that can be very detrimental because the target source is usually at least not in front of you, but either sitting next to you or behind you. So it would be good to have a steerable directionality. And with a binaural link, you actually can achieve exactly that. You can listen through the ear on your better side and just relay the signal to the other ear and gain through that. So that's one algorithm you can do. Or in the telephone condition, you can pick up the signal on one side and stream it to the other side and improve intelligibility. Or in wind noise, typically people tend to turn their head. So again, you have one better ear and you can pick up the signal. So when you think about it, there are quite a number of environments where you can make use of this principle of the better ear. And then there are other environments when the target is in front where you want a stronger directivity, and then you can use 4 microphones to combine and provide a stronger, more directive beamformer. and extract the signal better. And what I want to do in the following is talk a little bit about studies that we have done to test these two hypotheses. Do you have any questions or comments about the algorithms? I wanted to talk a little bit about studies that we have done to test. In one study, basically tested in a condition where you have a target in front and multiple noise sources around you. You test two different directional systems. One where the binaural directivity is off, and one where it is on, and schematically you see what should happen. If you turn the binaural directionality on, you should have a stronger beamformer and extract the signal much more and much better. And we did that with 20 adult subjects with a moderate to severe hearing loss, and we did basically various sets of experiments. We did a speech and noise test, but we also did subjective tests using listening effort scaling and paired comparison, so more an objective and more a subjective paradigm to test the performance of the algorithms. And that was, for example, a study that was done in Oldenburg. So something that could also be done at other hearing research centers and would be very worthwhile to look into. The setup of the sources was such that target was in front and noises were close. And we basically had two different paradigms. One was where the interfering noises were closer to the target, and one was where the interfering sources were a little bit further away from the target. And you would hypothesize that, especially in this condition, you should benefit more from the stronger directionality. And that's basically what we tested. And that's basically also what we find. So it's plotting speech intelligibility, SNR improvement for 3 different algorithms. And that's an older directional microphone, more modern, optimized monaural directional microphone, and the binaural directional microphone. And you find typically 1 to 2 dB speech intelligibility improvement in the condition. 1 to 2 dB is not gigantic like the 5 dB you get from omni to directional, but it again is an additional improvement in a pretty difficult listening condition. And for a speech test like that, the improvement in intelligibility is like 15 to 20%. So it still is a significant improvement that you find. And when you do a paired comparison test, you also see clearly that, especially in the condition when the noises, the interfering noises, are closer to the target, you find a significant improvement, also subjectively for people when they listen through it, for an approach like that. So that seems to be something that provides quite some benefit. Now, another study like this, basically more or less the same, was done by Erin Picou and Todd Ricketts, and they used a very similar paradigm. And they added also different room characteristics in a reverberant room, for example. And they showed that especially in the reverberant room, a significant portion of the people preferred the binaural directionality over the monaural directionality. So they also showed a similar result for this technology. So when the target in front, this can be applied. The downside of a technology like that is, and that's an interesting thing for me to know, is that people lose kind of spatial hearing, because what happens is you have the 2 hearing instruments, and at some point you add the 2 signals. And with that, out of a stereo signal, you create a mono signal. And every engineer, we put this on, immediately tears the hearing instrument off and says, "It will never work. You don't hear the spatial cues anymore." No hearing impaired people ever complained about it. They just I don't know, they just don't hear it or they ignore it. I don't know, I was surprised because this was such a strong limitation we thought, but nobody ever complained about it. And I would like to find out whether it's not a problem or whether they just ignore it or compensate for it or what the story behind it is. But I haven't heard big complaints. Yeah.
Have you got any idea if that translates out of the lab into the real world? That sort of feeling.
Yeah, I mean, for the engineers, you know, Volker, I mean, when he walks around with it, he constantly says, no, you clearly hear that you can't localize, but you compensate a lot by the visual sense, and then you have a spatial impression. But the feedback still is for all the audio-trained engineers that this feeling also persists in real life.
Do you think that it might be because for a hearing impaired person, their priority is to hear speech well, and that's more important to them than the spatial awareness, and maybe they've not had a great spatial awareness for quite some time anyway, so don't really feel they've lost it?
You know, that would have been a hypothesis from my end too, that maybe hearing impaired people for localization rely much more on the visual cues already, and then they don't realize it. But I still was surprised that I never got any feedback about it. So, you know, this is an example of where we thought we created a problem, but nobody realized it. We have another example where we solved a problem where nobody realized it, and that was with the real ear zoom. So today we are using the 2 microphones of a hearing instrument to recreate the pinner effect, so that people are able to tell front to back confusions. When we put that on hearing impaired people, they would immediately react and say, oh wow, I can tell front from back again. But they never ever would have complained about not being able to tell front from back. So
what's the moral of the story? Is it perhaps to not always believe your engineers?
Yes, yeah, well, that's absolutely one of the morals. And sometimes one moral also is that if you are convinced it solves the problem and market research doesn't show it, still stick to your opinion. Believe your engineer sometimes. So there is both sides. Okay, so I talked about the speech in front, and then what happens when the speech is to the side. So, for example, the car condition, and there was some work going on. Dr. Wu from Iowa, who tested moderately impaired subjects, 25 subjects, and he tested this algorithm listening to the side. And what they actually did is they took a car, they mounted a keyma into the car, and they had a driver, and then they drove around actually and made sound recordings in a driving car to have as realistic sounds as potentially possible. And they basically also did a speech intelligibility test, and they had 2 conditions, the target from the back and the target from the side, and they had 3 different settings. They had an omnidirectional setting, a directional setting, and this better ear technology. And it is pretty remarkable because this study also shows, and that was to be expected, that in certain speech and noise conditions, directional microphones don't provide a benefit. I mean, if the target is not in front, a directional microphone can negatively impact the result, and that's important also to counsel patients about, that they know about it. But it also shows that, especially when the target is to the side, the better ear technology provides quite a benefit for the patients in listening conditions like that. It seems to be a useful strategy. And the third application is an application where the wireless link is not built between the 2 hearing instruments, but between 2 hearing instruments and an external telephone. And that's a remarkable study Chase Wolf did, because it tested 14 moderately hearing impaired children at age 6 to 14 and at age 2 to 5. And it showed significant improvement in quiet and in noisy conditions between using a phone on one ear only, on the ear level, and a phone where the signal was streamed directly into the ear to both ears. And you see a big difference here in the speech intelligibility, but even more remarkable for me were the comments of the people participating in the study, because this technology suddenly changed the behavior of the people. And one problem, for example, was that the kids often couldn't communicate with their grandparents because they couldn't speak on the phone. But technologies like that made it possible for them to communicate on the phone and to start using the phone. And that was quite something for the family, that these kids suddenly could communicate. And such a small, if you think about situations you want to improve, and somebody comes up and says, I want to talk to my grandparent once a week, can you develop a technology? You would usually say, yeah, don't you have something bigger, something that you use 8 hours a day? But this made such a big difference to their lives that it's absolutely worthwhile. And it's worthwhile to look at situations like that and provide a special solution. That's the point I wanted to make here. And that's sometimes remarkable for me, that we often tend to have the approach to look at what are the big listening conditions, that you encounter often that we need to solve, rather to look at what are the most meaningful situations. Also this situation in the car. How often do parents drive their kids to school or pick them up from school? And it's only 10 minutes, 15 minutes per day, but it's a time of intense communication. And that's maybe an approach where we need to think about what are the really meaningful listening conditions, and what do we need to solve. What do we need to solve there? Yeah, I talked about that. So
exactly.
basically, today we have different technologies to help us improve speech intelligibility in various different listening conditions. And one point that is also always very important for me to make is that in modern hearing instruments, we already tend to develop specific solutions for specific listening conditions. So we don't develop this master algorithm that solves all the problems simultaneously, but we really try to develop what is a specific listening condition that we need to solve, and what can we do. So we have a portfolio of solutions for different listening conditions. In quiet environments, the omni microphone; in noisy restaurants, the directional microphones; in really loud bars, binaural directional microphone. You don't want to put that constantly on, because the wireless link drains the battery quite intensively, and you don't want to change the battery every day. So this is, you should switch this on when it's really a difficult listening condition. However, when you then change the distance between the hearing aid wearer and the target signal, reverberation and all sorts of effects come into play, and then you need other technologies than just the signal processing that we have in here. And so there are today various remote microphone systems that can pick up the signal and stream them in, and they just have also different performance levels. Certain remote microphones also have some, what I would call, audiological pre-processing. They adapt the gain depending on the environment noise level, and provide even a clearer signal. And with the introduction of the latest digital remote microphone system, there has been some progress made. And there has been a test by Linda Thibodeau and also Chase Wolf to test the performance of the devices, where you have the participant 5 meters away from the target source, and you would have the remote microphone pick up the signal here, and relay it to the hearing instrument here, and you would have a couple of interfering noises around it. And there are some remarkable differences. Already with traditional analog FM systems, you could achieve quite a significant improvement in terms of speech intelligibility, but it usually would roll off towards higher levels of background noise. And when you add a little bit of clever pre-processing, you gain quite some intelligibility. However, with the digital transmission link, you can significantly improve, especially in loud environments, all this pre-processing, the noise cancelling, and the gain adjustments that you can achieve. And even in louder environments, you can really achieve quite remarkable results here. And this is not too far away from what you sometimes encounter in school classes. 70 dB, 80 dB, sometimes it can get pretty loud. So digital wireless communication also on a longer range scale provides you quite some remarkable improvements. The first one was done with hearing instruments, and the second one was done with cochlear implants. So also in cochlear implants you find quite a remarkable difference. And the results that I showed earlier on about speech intelligibility improvement with binaural signal processing, we also repeated in cochlear implant patients. The only difference is in cochlear implant patients you find a difference of 3 to 5 dB. So they benefit much more from this technology than classical, conventional hearing impaired people. But both groups of patients, cochlear implant patients and hearing instrument patients, benefit significantly from technologies to help improve speech intelligibility in environments like that. And I think one topic that is becoming more and more interesting for me is all this auditory processing disorder. And I know we had quite some debate about it, whether it exists, what it is about, how to classify and characterize it. But I think for a couple of problems that exist, a couple of studies have shown that some of these kids can be helped by simply providing them with a clearer signal. Change their behavior, change their school marks and stuff like that. And I think that's maybe something that we should also apply more often and think more often about. Other than the classical noise-induced hearing loss application, what other audiological pathologies could we help with the technologies that we have at hand today? The wireless communication system certainly could provide some benefit for people with more auditory processing disorder type pathologies. Now looking forward into the future, I think besides what I talked now about, the major use case of improving ability to communicate and speech intelligibility in complex listening environments, wireless communication is going to significantly maybe also change the way we interact with the patient and how we provide the service to the patient. We could use smartphones and their connectivity to hearing instruments or any other mobile computing device for various other applications. You could stream information from the hearing instruments to the smartphone. You could tell the parents in which program their kids are. You could tell them how much they use the device. You could tell them what the battery status is and all sorts of things like that. So you could use it as an information and service center. You could simply use it to connect to other devices like public address systems in schools, in main stations, wherever. Or to your home audio systems, telephones and whatnot. You could use them as remote controls and more sophisticated remote controls, offering more potential to interact with the device and set it more precisely. You could use it as a training center You could use it for computation, so simply put functionality on the smartphone and not in the hearing instrument anymore. Or you could use them as a hub, for example, doing something like distance support. So the audiologist has a patient and the patient doesn't want or can't come back into the clinic. Now you could service them at home and have a Skype connection or wherever they are and help them troubleshoot problems, modify settings, and avoid or prevent them from having to come a long way back and look for parking spots and whatnot the problems are that they have to do. So distance support definitely is also something that that is an option for an application to help change also the provision channel. And I often was wondering whether approaches like this would help us to get a larger acceptance of hearing instruments. You know, maybe for some people they don't want to go through the process of always having to go to the clinic and see the audiologist, especially people with a milder form of a hearing loss. Maybe they want a simplified process where they go once to meet, to build up trust, and then some of the services they want to have done remotely. Maybe that would help us to improve penetration of hearing instruments too. So that's the future part. I think this wireless connectivity is going to offer us quite a lot of potential, also with respect to services and provision services in hearing healthcare. So with that, basically, I'm at the end. I wanted to talk a little bit about the binaural signal processing strategies and talk for a second about how actually they mimic a little bit what the human auditory system does, and that they provide communication benefit in various listening conditions, like when the target is in front or the target is at the side or the target is on the telephone. Or also over larger distances. And when we have hearing instruments with forms of wireless connectivity built in, it's always important to consider for what use case are they designed. Is it just a streaming use case, or what's the objective that you want to do? And today's systems really, I think, also provide benefit in terms of hearing performance, which is very important. And whatever I said basically applies for both hearing instruments and cochlear implants also in the future. Yeah, with that, I'm at the end, and thank you for your attention.
Thank you, Stefan. And for any questions? Yeah, Michael.
Actually, picking up on your last thing there, then, one of the problems with audiology is that you're putting on so many different transducers and taking them off again, and then you're doing your couple of differences and all the other things like that. So are you looking at, say, actually like a smartphone combination can actually use as an audiometer, and that you're only going to be able to do AC initially, but you've at least got your calibration on your production line of your receivers, so that you could actually do remote audiology?
So what is it exactly that just use the smartphone and the hearing instrument to do an audiogram?
Yes.
Like a direct audiogram of the person?
Yes. Well, you could do it remotely. I mean, once you've gone to the basic clinic audiometry on the hospital grade audiometer, you could then monitor remotely.
Yeah. That would, for example, be one application. Or you could build in a self-test into the hearing instrument to continuously measure where they are at and develop a calibration strategy. But with the smartphones in the future, we will have a lot of potential to also measure auditory functions and test.
Okay,
could you go back to this slide about where the children did really well on the phone? Okay. Oh, okay. So these are the older children. Do you remember what the younger children were like? Oh, there you go. Something you prepared earlier.
I just wanted to.
That's fine. Yeah. Yeah.
And also the younger children, especially in a noisy background, gained quite some benefit.
Very good.
Yeah, and especially for the younger group, this emotional comment of it changed our lives was much stronger. Yeah.
Just one point I want to make for the audiologists in the room. I mean, it's great that the hearing aid manufacturers are thinking about this improvement of lives, and it's just to remind the audiologists and trainees in the room that audiologists must get that information off their patients.
Yeah.
That, you know, it's the key part of our job is to find out what is the most important thing.
Yeah, but you know I'm stealing your time, Kevin, but
No,
you know,
it's all got
for me,
5 minutes.
this is again something which I love in the future about these devices, because we basically have developed a technology today where you as an audiologist could send out a questionnaire to the hearing impaired person or the parents, and you could interact with them while they are not in the clinic. You could interact with them, you could ask them questions, you could remind them, and I think exactly this wireless connectivity might help us in the future to better interact and help the audiologists to better understand what their listening needs, their problems, and so on are. So I think that's very important.
I just have a practical question about the batteries. Do you charge these hearing aids, or do you have to change the batteries every time?
No, you have to change these batteries. And one problem with the rechargeable batteries is that it's two problems. Often the rechargeable batteries don't stand the peak currents. When you're in loud environments and you have a wireless system on, the system draws quite some power, and it's like 20 to 50 times more than in a quiet environment without the wireless system. And the battery has to be capable to take these loads, and most rechargeable batteries just die.
So what's the comparison between the old style hearing aids? What's the comparison between the old style hearing aids, battery life, and the new ones?
It depends on the usage pattern. If you switch on the same set of algorithms with a new hearing instrument, then the battery lifetime is like twice as long because we have better technology. However, if you use all the bells and whistles we have added, plus the wireless link, the battery consumption can be twice as much. So
it should be how much?
Today, typically, we calculate with specific usage profiles, like 4 hours a day of wireless streaming, and then it should be 4, 5, 6 days. Anything from 3 to 10 days. Very much depending on how much do you use this wireless link.
So it can be quite expensive to be able to hear people properly.
Yeah, I know. That's one of the downsides, clearly, with the batteries. And I don't have the picture here now, but the problem with the modern electronics is that the computational power increases like this, and the battery power like this. I asked battery manufacturers, how did the battery capacity change? Can you give me a plot how it changed? And they said, yeah, it's very simple. It's just a flat line. So basically, over the past 10 years, battery capacity has not increased. That's a problem we fight. And I know it's a problem for the patients.
What about then using the 4 microphones to form the more accurate beam? Is that just a straightforward doubling of power to use those 4 microphones as opposed to 2? Or
the major difficulty of the 4 microphones is not in the signal processing or the power consumption, but it's in the link.
Right.
It's sending the audio signal from here to here through the head. That's where the power drain comes from. And it increases the power drain from being 1.5 milliamp to 2.5 to 3 milliamp. So it's maybe 80% more. It's significant. That's why we don't always switch it on.
So how far away are we, Stefan, from providing hearing instruments that help normal hearing people in noisy environments?
I think a normal hearing person already would benefit significantly from using a remote microphone. But I think the trade-offs that we have to make with putting the device on, wearing comfort and things like that, still probably are too large. But I mean, even if I put on a hearing instrument with closed ear moles in a speech intelligibility test, I do significantly better than without.
In background noise?
In background noise, yeah. So you do better already, but it's, you know, this trade-off, the sound quality, your own voice, you don't want your ears blocked. That's when you use the full capacity of the system. That's the problem.
I mean, it would certainly, I imagine it would crack the stigmas of you wearing a hearing aid if normal hearing people got benefits. It's no longer seen as a crutch, huh?
Yeah. It probably would help.
So I think that we can wrap up at that stage. So thank you very much for coming along and supporting the seminars. There's another one next Thursday. I'm the speaker here. We've got a bad habit of every week saying, who's speaking next week? We'll learn next week who to introduce for the week after. But thanks for your attendance. I think it's time to give you lunch. And so thank you to Stefan.
Thank you.